Hello once again, class, and welcome to another mock lecture. Today we're going to be talking about the normal distribution, the typical bell curve, if you will. And we're going to start off by talking about the different shapes of graphs, the kind of different distributions that there are, and then the last one we'll get into is normal distribution in a fair bit more detail than the other ones. These are the five, right, that we'll talk about. And for all of these graphs, all of these different distributions, what we're talking about is the data values being on the x-axis, so like the actual value of whatever data that you have. And then the undrawn y-axis is going to be the frequency at which those data values occur. This one's called a skew right distribution. This one's called a skew left distribution. This one's called a uniform distribution. This one's called a bimodal distribution. And then finally we have the normal distribution. So we'll talk about these kind of one at a time and end with normal distribution going in a bit more detail. Because there's a bit more to talk about with normal distributions. So we'll start with skew right. When you have a skew, what that means, I think about it mostly as like a taper. So for me, a skew is like tapering to some direction. So if it's skewed right, then the frequencies of our data points are tapering off as you move to the right, right? That's where the tail end of the graph is. That's another way that I think about it, as a tail end. But skew graphs are interesting for a couple of reasons. Number one is that in a skew right situation, the most frequent data is on the left end of the range. So the range here goes from like 1 to 10, and we have a lot of frequency in this example, in the 1 to 3 range, and not a whole lot of frequency, past 3, really. There's just one of some numbers that are kind of past there. So it is true to say that the most frequent data appears on the left end of the graph. But as far as the most cumulative data, that is usually on the right of the mode. So you have like your most frequent thing, and maybe our mode is, in this example, it's 2. I know this graph isn't exactly what's going on. In fact, I'll show you this graph in a second. But in general, you can think about a skew right graph. The mode is on the left, because that's where the most frequent data is. But then past the mode, there's like cumulatively more data on that side than there would be on the left side. So the most frequent data is on the left, but most of the actual data is to the right of your mode. That's a skew right situation. The graph of this one looks like this, and you can kind of see that's happening here. There's like a tail, as it were. You're tapering off to the right, and so tail on the right. Anytime I see that, that's a skew right situation. Skew left is similar, but in an opposite way, right? Now, most of your data is actually to the left of the mode. But again, the most frequent data, right? The data that has the most frequency is now on the right end of the spread of the data. So most frequent data on the right, but more data to the left of the mode. And again, you have to think about it in terms of a taper. You're tapering off to the left. Your most frequent thing happens somewhere on the right. That's where your mode is. So in this one, what we're saying is there's actually more data. And here we can actually use the actual example, right? Our mode's here. I'll just kind of fill it in here. There's more data to the left of the mode than there is to the right of the mode. But the most frequent data happens on the right end of the graph itself. That's skew left. And again, I think about it in terms of there being a tail on the left end, a tail or a taper. The next distribution is called a uniform distribution, and there's really not much to say about this one other than the data is, spread relatively frequently, right? Relatively evenly, I should say, over its range, right? There's the same amount of every type of data point, basically, and, that gets you something that looks like this. A perfectly uniform distribution will just kind of look like a rectangle when you draw the histogram, right, for that particular data. The next one's called bimodal, and again, not too much to say about this one. You usually find two kind of clusters of data when you have a bimodal situation, and they're usually kind of around the two modes that you have. So this one has a mode of 3 and another mode of 7, and we kind of see a clustering of data around those two things. There's two peaks. That's how you always know you're looking at something that's bimodal. Which finally brings us to a normal distribution. And then here's an example of some data that is normally distributed. You've got your mode, which is 7, And then you have kind of the same amount of data on either side of the mean, right? We've got 6 data points here and 6 data points here to the left and right of the mean. Now I know what you're thinking. You're thinking, the mean? Don't you mean the mode, Mock? Like you just said mode, but now you're saying you have two, equal amount of data on either side of the mean. Well, that's the second cool characteristic about a normal distribution. In a normal distribution, the mode, the median, and the mean are all the exact same number, which is cool. No matter which measure of center that you use, that is the center of your data, and you have the same amount of data on either side of those things. And what this creates is a symmetrically distributed frequency chart kind of around the mean itself. In this case, our mean is 7, and so we have the same amount of data points to the left and to the right of it. It's symmetrical, right? We should be able to fold it in half essentially along the mean, and the graph will line up with itself. So we're going to talk a little bit in more depth with normal distributions, because this one has what I would say the most characteristics among the 5 that we kind of just introduced here. So first, to make things easier to look at, we're going to simplify the histogram into being this curve. This is called a bell curve. That might be something that you've heard of before, and whenever you hear a bell curve, what they're talking about is data that's normally distributed. What you do is you have your mean right in the center, which again is your median and your mode. So it's not only is it the average of all of the data that's within this distributed data set, it is also the most frequent thing, right? It's also the thing that happens the most, and it's also the thing that's exactly in the middle if we were to order all of our data. We give the mean the Greek letter mu. That's what this is. So anytime you see mu, you know that what we're talking about is the mean. Then what happens is the distribution is broken up into some number of these things called standard deviations. And the way that we denote what a standard deviation is again with a Greek letter. This one is the lowercase sigma. So anytime you see this, you have to think, oh, we're talking about a standard deviation. And so what I did here is I moved some number of standard deviations away from the mean. So like this is 1 standard deviation to the right of the mean. This is 2 standard deviations to the right of the mean. This is 3 standard deviations to the right of the mean. And over here you have 1, 2, and 3 standard deviations away to the left, right, of the mean. But a standard deviation, right, because you might be wondering, what in the heck is a standard deviation? Essentially, it's a distance. A standard deviation is the average distance that any data point is away from the mean. So because of the way that the data is distributed, we know, based on these number of standard deviations away from the mean that you are, that there's certain percentages of your data contained within these standard deviation intervals. And so here's kind of the main idea. When you have data that's normally distributed, we know that 68% of your data is within 1 standard deviation away from your mean. That could either be to the left or to the right. So if you split that in half, you can say 34% of your data is 1 standard deviation to the right from your mean, right? It's within 1 standard deviation away to the right of your mean. And another 34% is 1 standard deviation to the left away from your mean. But collectively, right, around the mean, around 1 standard deviation away from the mean in either direction, 68% of your data is within that particular interval, within mu minus 1 standard deviation to mu plus 1 standard deviation. So more than half your data is here in the kind of middle of the graph. If you move another standard deviation away to the left and to the right, there's an additional 13.5% of your data within that next standard deviation away. Okay, so that's what, 27% of your data gets added on to the 68% as you move 2 standard deviations away. So we're only 2 standard deviations away from whatever the mean is, and already a vast majority of our data is within this interval, within mu minus 2 standard deviations to mu plus 2 standard deviations. As you keep going further out, there's less data that exists out here. And that's just how normal distributions exist. That's just how they are. And we know the percentages have to be the same on either side because normal distributions are symmetrical. So within 3 standard deviations away, there's 99.7% of your data, which means there's only 0.15% of your data to 3 standard deviations away on the right and 3 standard deviations away on the left. There's like hardly any data this far away from the mean, right? Some people will call these outliers. There's actually a mathematical definition for an outlier, which we're not going to get into. But, when you're this far away, you're in pretty rare territory as a data point. So what I want to do is I want to go through some examples utilizing these percentages so we can get an idea about what the point of all of this stuff is. All right, so example number 1. In the 2009 Wimbledon finals against Roger Federer, Andy Roddick had an average first serve speed of 127 miles per hour. We're going to assume that his speed was normally distributed with a standard deviation of 5 miles per hour. So anytime that you're given that some amount of data is normally distributed, you want to first draw your bell curve and put your mean right in the middle, right? We know the mean is 127 miles per hour. Now we also know that the standard deviation is 5 miles per hour. So each time we move one standard deviation away, or another standard deviation away, or another standard deviation away, what you're doing is you're adding 5, right? That's a distance. 5 is your distance here. In this case, it's 5 miles per hour. So as we move up to the right, we have 132 is 1 standard deviation away, 137 is 2 standard deviations away, and 142 is 3 standard deviations away. And to go the other way, you subtract a standard deviation. So 122 is 1 standard deviation away to the left, 117 is 2 standard deviations, and 112 is going to be 3 standard deviations. So now we have our model, right? We've drawn 3 standard deviations out in either direction. So we can start answering some questions that might get thrown at us. So the first one says, what % of serves were between 122 miles per hour and 137 miles per hour? So remember, we have all these percentages that exist in these, intervals, right? Like here's 34% of data, right? Here's 34% of data. This is 13.5% of the data. Another 13.5% of the data. Excuse my terrible handwriting. Both of these are 2.35%, right? And then the last one is, let me get my percent there, 0.15, right? Percent exists in these really tiny spaces here. That's 0.15%. Well, we're looking at between 122, that's here, if I could draw a straight line, to 137, to here. So if I make this look nicer and shade this stuff in, we're looking at this. This shaded region represents all the data that is between 122 miles per hour and 137 miles per hour. So what percent is this? Well, you just add up all the percents. So it turns out 81.5% of Roddick's serves were between 122 miles per hour and 137 miles per hour. Okay, next question. What percent of serves were at least 132 miles per hour? Well, at least means that's the slowest serve, as it were, that he ended up serving as his first serve. So the lower bound is here. That's the lower bound. Everything above that would be considered at least 132 miles per hour. So we're looking at all of this stuff. Again, we just add the percents together. 13.5 from here. Collectively, this is 2.5 because 2.35 plus 0.15 is 2.5. And I only did it like that because that was easier to add. You get 15 plus the 1 that you get from the halves, so you get 16%. Next one. If Roddick had 120 first serves in the match, so let's say he served 120 first serves, how many were at most 137 miles per hour? Now, at most is different than at least, right? So first we have to recognize this. At most means now this is an upper bound. So it actually represents all of this stuff, right? Everything that's to the left of 137 miles per hour. First, we should figure out what percent of the data that is. So again, it's all of this. And what we could do is you could add up 0.15, 2.35, 13.5, 34, 13.5. Or you could realize, well, wait a minute, this right here is just 5%. The whole thing's 100, so we'll do 100 minus 5. So all of this stuff that I've shaded in is 95% of the data. Now that we know what percent of serves were at most 137 miles per hour, let's just find of 120, what's 95% of that? And that would give us the number of first serves that were at most 137 miles per hour. And so we get 0.95 times 120, which is 114 first serves. Okay, and the last question says, if Roddick had a first serve speed of 110 miles per hour, would that be unusual? Well, if you look at the data, 110 is further than 3 standard deviations away from the mean to the left, right? This is really, really slow for redux standards. More than 3 standard deviations away, only 0.15% of the data exists here. So yeah, this would be highly unusual in the sense that like there's barely any data points out here. Of all of the however many first serves he had, and we can even go with 120 of them, only 0.15% of them were less than 112. And maybe 110 is like the only one that's out there. Maybe he did like a kick serve as a first serve or something. But anyway, that's how that works. So, and I'm only going to go through this one example because I think this is all we need. Whenever you're dealing with normal distributions, the first thing you want to do is draw your bell curve and draw 3 standard deviations both to the left and the right, and then you just have to remember your percentages. Okay? Bonus content. All right, so let's say that you have some data, right? There's some data that exists here, and we want to figure out a way to organize this a little bit better, right? I've already went ahead and I've ordered all these data points, but here's something that you can do. It's called a stem and leaf plot. First thing you're going to want to do is you're going to want to draw a vertical line like this. The next thing you're going to want to do is put in all of your stems. Now, in this particular case, we can make the tens position your stems. So we've got 1, 2, 3, 4, 5, 6, because those are all the tens positions that we have in this amount of data. Your leaves then would be all the ones positions. And what you do is you write them to the right of this vertical line, usually without commas, and you write it with the frequency at which they appear. So here's all the leaves for this thing, and the thing I want you to pay attention to is that 10, 10, 11, and 12 are all data points. So you have 10, 10, 11, 12, right, as data points, and that's how that works. So for 2, you got 21, 24, 24, 24, 25, 27, 27. Well, that's listed here, 21, 24, 2. Wait, why do I have 22 on here? Okay, that shouldn't be there. 24, 24, 24, 25, 27, 27. Right, for 30, you've got 30, 33, 35, right? 49 is on there. There's no 50 at all, so notice there's nothing listed here. And then 61 and 68, so the 1 and the 8 are in the leaf position, okay? The other cool thing about a stem and leaf plot is if you just rotate it 90 degrees, now you're looking at a histogram. But pretend that those aren't there. All right, so that's it. Hopefully you guys learned something. If you have any questions, please leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.